What was amazing to me was when Stabler showed the comparison between birds and human language. Can you talk about that for a minute?
Yeah, well, that's part of the, what
Yeah.
that's part of what our what the people who are engineers that are working with our project are involved with. In English, some words like a, the, and are very common. Other words like frigate, you don't hear very much, and anti-disestablishmentarianism, you hear practically never. And if you plot the frequency at which you hear something against the rank order of the words, there's a straight log-log plot. That's called a zip curve. And the birds have the same thing.
Identical.
Almost identical. And, which is, kind of neat. And their vocabularies can approach not human words. Humans have, even a young child will have thousands of words in their vocabulary. But these will have certainly hundreds. And one of the species we were working with this morning has certainly 800 phrases in its vocabulary, and probably
thrasher?
more. The cat
thrasher.
thrasher.
Amazing.
Although they only work with 30 or 40 typically at a time. But they'll work
Just
with
like
one.
humans.
They'll work with one 30 or 40, then they'll go to another 30 or 40. Sometimes they'll go back. Sometimes they'll go to another 30 or 40. Stabler thinks he has identified the main probabilistic description of their grammar. I haven't seen it yet. He just told me about it a week or two ago. But that's what we hope to do. And if we're going to hear things, identify words from here automatically from this pattern, then we have to have pretty good word recognition. We teach them. Typically, we teach them. To teach the machines to recognize. So we'll give 20 examples of AA, 20 examples of AB, 20 examples of AC, and so on. And if we give them 20 examples, well, even I could teach a machine with 20 examples using the same technology that's used in these miserable give your credit card number programs on the telephone. That's called a hidden Markov model. And then down to, say, 15 examples using what are called support vector machines, where you teach it to use other ways to distinguish them. But we could get that to work too. An undergraduate from engineering helped me do that. But the graduate students in engineering now, using from the speech recognition lab, they can get down to 4 or 5 examples, and then they have 95% or better recognition of that word in the future, that phrase. So we're pretty excited about that. I don't think it'll work quite so easily with this species, but with the species that they're working with, the vireo, which certainly has 200 words in their vocabulary, phrases in their vocabulary. It works 95% of the time or better. And we're trying to automate it so that we can just, they can be doing a recording, and then it'll spit out AA, AB, AC, AG, BA, DD, and so on. We're not at that place yet. All the recordings aren't as pretty as this, and I'm recognizing the boundaries here can be challenging, especially if there's another bird in the background. That's called the segmentation problem, that's called. But that's what we're working toward, and why the engineers are engaged with that part of it. Others are engaged in another part of it for your thing, setting up for that. We have to know who is who and where they are, not just what their direction is. We have to know who they are. So what we've done toward that goal is working with one of my students who was originally from Caltech, got his degree here, and then he worked with someone who's now at MIT to make these things.
I was just going to ask.
These are the
if-
sensor arrays that we're trying to teach and to work with. So here you see 1, 2, 3, 4 microphones. And so if Victoria says something, these 2 microphones will hear Victoria first. If I say something, this will hear first. And so looking at very subtle differences in timing and in phase shifting, you can identify where something is coming from. And if we have 8 of these around, we can identify to within a meter where the bird is. And even in 3D, we can identify within a meter where it is. Let me show you the recordings we made this morning with this.
So if you imagine 8 of these sensors placed around, and then they can dimensionally record the conversations, you can start seeing how mappings and rhythms of communication can be mapped. And basically that's what they're working on.
Yeah, the birds, it's kind of neat. The birds we wanted to hear this morning, when I was setting up, we had a black-headed grosbeak who we heard, and I just played around with. I played with my iPhone, and he came within 20 feet of me, right above me. It pulled him in. He didn't like hearing another black-headed grosbeak in the territory. And his wife, his mate, was right in the tree, maybe 20 feet away. And then after that, only when I had this thing turned off did we hear the birds, the grosbeaks. But we heard another that with a nice, rich vocabulary. But here's another species that was the most
drama.
common.
Like who's in my territory?
You remember this, Victoria? Hear another one in the background? Let's do it again. And by analyzing these differences here, one could do timing, and one can do phase shifting. Sometimes you may, when you want to hear something better, you'll turn your head. So that the phase differences in the sound waves will be maximized, depending on the frequency when you do your head this way. So even if it's coming from there, you'll turn your head so that you can get the phase differences. Well, that's what some of my students have written. My students, and especially students in engineering, a different engineering lab, have written software that, based on those traces up there, they can identify things to within a meter over a 300 meter by 300 meter area. And also, we're just exploring the 3D. We have it working in some cases in 3D, other cases not so well. But generally speaking, working in 3D. And the idea is then that pretty soon we'll be able to put a bunch of these out, and they will hear all the different phrases, and then we'll know who's doing what. Well, we don't know who's doing what. We'll know who's where. And vocalizing. And if we sit and keep track of what they're doing, then our hope is that we'll be able to tell. The first things we'll look at is one of the species we're studying. We know that if a male is singing here, and another male may come that's in a neighboring territory, he'll come right over to the edge. They'll both go to the edge. And then they'll start phrase matching. So if one says A-A-A-B, the other one will say A-A-A-B, even though he would have been doing C-D, G-F, R-M. The phrase matching, very aggressive.
Echoing, yes, I've seen that. And it's really, there's something exhilarating about playing the sound and hearing the bird respond to you with the same sound. It's amazing somehow.
It is.
It really is.
And remember, you heard 2 of them? You see this one back here? Well, you've probably observed yourself, or if you haven't, you will observe now that in male-female interactions, the males will often, humans, the males will talk, it's like a dominance thing, talk on top of the female. They'll interrupt. Females much less frequently interrupt males. And in males, dominance, look at the dominance. You'll see the guys that want to be dominant come in and they talk on top of somebody else. And these do exactly the same thing.
Is that right?
Exactly the
We're
same thing.
just like birds.
Or
But
they're
then
like
there's group of women. That's the dangerous ones. So one male in the class.
yeah. My students are all males.
I will repeat your question, by the way, just for the tape.
Okay.
So
I have two questions. One, isn't that dominance thing variable depending on culture too? Like some cultures, I know in the West it's like really common for like males to speak first and to interrupt and stuff, but not so much in other, like Eastern cultures.
Asian, very different. But it can be equally aggressive.
Just different ways.
Yeah, Japanese. I had to have a Japanese professor explain to me. Japanese may seem very polite, but underneath it's like this, and it really is.
very rigid, actually.
Yeah, you just have to learn the rules. Do they do it? I don't know. They have certainly many species of birds have dialects. One of the most famous studies of this was up in the San Francisco Bay Area, and so there's a Golden Gate, Alameda. What's the park in Berkeley? It's up in the hills anyway. Raspberry Creek and Marin. They all have very different dialects. And
That's right. And you said that the birds, the thrashers in Southern California, have less of a vocabulary than those in the north.
that was seemed to be our
Because
belief
they're
so far.
chilling, they're hanging out.
That could
But
that
I
seems
thought
to
that
be.
was really interesting.
That's based on a small sample size, but that's what we're finding. And so there are dialects, and there could easily be dialects in behavior. I don't know.
My other question was at what point does one bird like back down or get tired of matching the other birds or the other male birds?
So I'll repeat the question. At which point do the birds back down from matching the one from the other or to the other?
Okay. Well, we ourselves have not studied that, but it's a classic problem in the application of game theory and behavior called hawk-dove. And here's the game. If you have two hawks, well, let's say we have a hawk and a dove first. A hawk and a dove. They come together, they want the food. And the hawk will always take from the dove. The dove will always back down. That's called the dove behavior and the hawk behavior. And in that case, let's say the hawk gets 2 points and the dove gets 0. If you have a dove with a dove, they'll each get 1. If you have a hawk with a hawk, neither one will back down, and they'll both beat each other up, and they'll get -1 for the confrontation. And the question is, what should you do? What should the birds do in these circumstances? And the answer is, if you always back down, then everybody will take advantage of you. If you're always a hawk, you'll get bejesus beat out of you. Just, plenty of bars where you don't want to be a hawk. And so what's called for is a mixed strategy. And you I don't want to say flip a coin, but effectively that. You use a mixed strategy that's probabilistic, that's going to depend on the payoffs.
Pick your fight.
Pick your fights.
You pick your fights carefully.
Carefully.
Yes, exactly. And do they do this? Well, I saw an analysis last week that said, yes, they do back off, and that's with the territory holder. The territory holder almost always wins. And so when they have neighboring territories, in this guy's territory, this guy will always back off, will eventually back off. In this guy's territory, this guy will back off. And of course, do they shift the territory boundaries? That's, I don't know how that's done, but there are rules, for sure.
So can I make it a full circle back to consciousness?
Yeah.
Which is where we started. How is this research informing your initial quest that continues? How are you feeling like you're enriching or understanding consciousness better through this interaction and study of the bird communications?
At the current time, I really don't know how to think like a bird. I'm getting better. I can think like a dog lots. And I have a hard time thinking like a woman sometimes. But dogs I do better with.
So men are closer to dogs. That's what you're saying.
Birds I'm getting better with. But I think that we're approaching a better understanding of their language. Mm-hmm. Certainly their syntax, we're really starting to get substantial progress in that area. And I think we're right at the forefront. We may be at the front because of the linguists that we're working with. Yeah. And the computational methods that really weren't available up until now. Mm-hmm. This uses a lot of computation time to analyze these. But that will, so if we can understand their language, then that's a first step toward doing the grounding problem, which is the 500-pound gorilla. No one has managed to do that yet. But in theory, we can do it. We know that. We had a graduate student that he's now at the University of Chicago, but he proved that using our methods, in theory, with infinite amount of recordings, we should be able to do the grounding problem. Oh. And hopefully we'll get toward that. Yeah.